Hello guys, welcome to another video. This time I'll be basically going over the complete mechanics syllabus, concising it down a lot so that this can work as your revision guide uh 2 to 3 months before your exam, so that you can get down and start working on papers because A2 most important thing is solving question papers, right? So, okay, so the A2 mechanics syllabus. Okay, the A2 mechanics syllabus, uh, there are a few things you have to know that there are 9 chapters in total. One of them being first one being velocity and acceleration. Second one being forces and motion in one dimension. Excuse me if my handwriting is kind of bad. I'm very new to using the tablet. Otherwise, I hope to write it in a way that everyone can understand. Then we have forces in to dimension. Then we have friction. Chapter 5 is connected particles. Connected particles. Chapter 6 is uh general, I think it was general motion in a straight line. There you go. Chapter 7 was momentum. Chapter 8 is work and energy. And finally, chapter 9. Oh, oops, sorry. Right. And finally, chapter 9 is work, energy, and power. Or a lot of people say the work, energy, power principle, but at the end of the day, whichever one makes you comfortable. So, mm, before we start, I'm going to give you guys a little bit of overview on which one's very easy and which ones like are kind of hard. So, uh, in your M1 question paper, okay, a little bit about the question paper here. Um, your question paper is of 50 marks. Okay, and there are, I think, every year, number of questions are 6 to 7, 7 being the highest and 6 being the minimum. And usually, usually you'll see that most of the topics are quite straightforward, uh, and you can get marks very easily. Mm, uh, in the first 3 questions. I think usually question 1, 2, and 3 are ones where they'll give you easy 25-ish marks. So question 1, 2, 3 equals 25 to 30. No, actually it's 25 marks, not 30 marks. 20 to 25 marks, yes. Um, yeah, 20 to 25 marks. Question okay, wait. Considering question 4 and 5 usually have um 10 to 12 marks, and question 6, 7 have, I think, 10 to 15 marks, depending on the intensity. So overall, mm, a combination of this always adds up to 50. Uh, Question 6 and 7 is usually always general motion in a straight line question or a work energy principle, but again, they shuffle it every year, so it doesn't matter. But yeah, I gave you the basic idea. So let's move on. Okay? So yeah, right. What we're gonna do now is we're gonna go topic wise. I'm going to show you literally everything you need um in this video so that you can sit down. Um, by the way, make sure to note everything down so that when you sit down solving papers, you can look back at this note and come back to it every time you get stuck. There's a lot of I'm just an indicator, but you'll see there are more hundreds of videos by lots of YouTubers who solve question papers, and they're very good at it. Um, I'll give you some examples. Since I'm already working on that, might as well tell you. I think I mentioned this in another video of mine. Uh, uh, Best YouTubers for papers. You have, I think, people who come at the top of my brain are have Zane, you have Zane Matix, you have Si Xiang Hung. I hope I'm pronouncing the name correctly. You have I think who else? You have Math 64 and you have I think oh yeah, you also have Xenox. Yeah. So that's that. Maybe I'm missing a few more, but yeah, for now I think that's the one. Those are the ones I think I used back in my during my exam days. I think you also have no, I think these are the ones. Yeah. Oh, wait, of course, for of course. You have saved my exams. Think uh these ones are the best in my opinion. This one, and this one. These are the best, right? Okay, moving back to topic. Um, One more thing that you should know. Uh, Chapters that are very straightforward are this. Oh, sure. Wait. I won't say this. Yeah, chapters that are very straightforward are chapter one, chapter two, definitely chapter three. Friction sometimes get can get tough, but that shouldn't be an issue. So friction, connected particles is a topic that we have to delve further into. General motion and a straight line is fine. Momentum, work and energy, and work energy and power. So the thing about momentum, work energy and power is basically there's a problem with it. It varies from year to year. Sometimes you'll see that work, energy, and power, chapter 8 and 9, have combined question in question 6 and 7 of the question paper, and they're very hard. They're like one of the toughest questions to solve. In some years, you'll see that they are the part of the question 1 and 2, and you'll get easy questions where you can easily get 10 full marks. Momentum is one of those very special topics as well, because people who understand momentum usually can solve every question. But the thing is, momentum sometimes also uh, pairs up with uh, other topics like friction, forces in a two dimension, etc. Sometimes even work and energy. So it gets very confusing because the maths become very long. So yeah, without further ado, let's get started. Okay, all right. Okay. So, um, so chapter one is velocity and acceleration. velocity and acceleration. So, right. Now, excuse me. Where is it? All right. So, for velocity and acceleration, there's a few things that you have to know. Hmm. It's very simple. It's one of the most straightforward chapters. So you have constant speed, constant speed. That is S is equals to VT. You have and you have constant acceleration, for which the formulas are S is equals to UT plus minus half AT square. V square is equals to U square plus minus 2AS. Okay. V is equals to U plus minus AT. And and S is equals to U plus V by 2 times T. Right. So these are the ones. Now, most of these are pretty straightforward. Like the first one is about distance, the total distance. Second one is about final initial velocities. Third one is also about final and initial velocity related to time. This, however, the final one, this one, uh, this one, this is regarding, this is regarding average distance, right? Average distance. Actually, no. This is regarding average speed to find distance, right? Okay, I think that's that. Hmm. Is that it? Yeah. Actually, I don't like how I wrote that. I want to write it in a better way so that people understand. Okay. Average speed to find distance. Right. Okay. Because you're averaging the speed of final initial. Uh, yeah. Okay. So this was very simple. Gonna give you guys some like I'll give you guys a bit more to time to understand while a lot of you might not understand a lot of things, but I'll break it down. I think this color should looks better. So uh yeah, S means distance, but can also mean displacement. Maybe in school you learned this as D, but the actual terminology is S when representing it. V is final velocity. U is oh shoot, right. S. U is initial velocity. Um, T equals time taken. All right. Okay, I'll also write the meter per second, meter per second, second, and x a is acceleration, of course. So, right, I annotated the symbols, wrote their meanings, and gave their SI units because SI units are what you'll be mostly working with unless stated otherwise in the question. Okay, moving on to moving on to chapter two. Right, moving on to chapter two. Chapter two. This is forces and motion in one dimension. Forces and motion in one dimension. Oh my God, I really have to sometimes work on my spelling. Dimension. Now, right. So this is that. First of all, oh, oops, my bad. This. All right, draw. Now. So this is also a very straightforward topic. Nothing to mainly talk about. because this is all you've learned in O levels as well. So first formula is forces equals to mass times acceleration, which is F is equals to ma. Unit is actually not now. Yeah, I'll just give you the formulas now and later on I'll tell you. All right. Then, weight is equals to mass times gravity. W is equals to mg. Finally, this one might be a bit new, but you should learn this. Normal contact force, which is equals to mass times gravity as well. Okay, which is R is equals to mg. Now, for those who don't understand normal contact force, of course, this is very new. This is like very, 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 very new. Right. So as we go further down, you will understand that normal contact force has more significance than you think in A2. And a lot of people, I mean, you might be thinking that this is as similar as it seems, but let me tell you, it's not. So what is normal contact force? I'll just give you a little brief on it. I'll not really explain what's up, but I'll just give you the idea. So considering this is a box in a horizontal plane, horizontal plane as in like a flat plane. So if weight is working downwards, normal contact force, denoted as R, is working upwards. As the box is stationary, we can say R is equals to weight, which is equals to mg. However, do not think it is as simple as this because it does get complicated. Anyways, moving on. Okay, so again, I'll detonate everything for you guys because yeah. All right. Oh, where's the red button? Sorry, guys, I'm very new to this again, but I should be good. Okay, so F is equals to force, or some people like to say resultant force, but whatever, it's Newton. Is equals to acceleration, which is equals to meter per second square. Did I? Oh, this was wrong. Um, thanks that I caught it. Yeah, it's meter per second square. Uh, what's next? Yeah, mm, M is equals to mass, just kg. R is equals to normal contact force, which is also denoted with, I think, Newton. Right. So that's that. Now, moving on to chapter 3. Chapter 3 is where this is dealt with in a more I feel like it's more we go further in chapter 2 in chapter 3 and we discuss the forces, specifically all the forces that acts on an object further, more deeper. So it's forces in two dimension. Now, excuse me because there is going to be a few drawings in this one. So I don't know. I might draw well, might draw bad. Who knows? Excuse me. Okay. So right, right. Now we learned in oh shoot. Wait. Cross this out. We learned in AS physics, right? AS physics, right? about forces in two dimensions, I think, during in chapter two, I think. Right, why is it not going? Oh, right. So, what did we learn in physics? I think this, that if force is acting at an angle, theta, you can resolve the forces perpendicularly, one being F cos theta, F sine theta. A very common way to think, a very common way to understand which one is cos and which one is sine is look at the cos theta, right? If you look at if you look at cos theta, you can figure out that sorry, if you look at theta, whichever side theta is touching, that side becomes cos theta. And if this side is cos theta, the other side, of course, becomes sine theta. That's how my teachers taught me, and that's how I like to think of it as well. Oh shoot, my bad. Oh, I think you undo here. Hmm, right. Oh, right. But yeah, this is theta. Okay. Now, this would be resolving forces in two dimensions. Now, don't get me wrong, there is not a single formula that I can teach you here because forces in two dimensions exactly work with the same formulas that were taught in chapter 2 with a slight modification, all right? Which you will only understand when you do question papers. This will help you. You can use this as a reference. So that's that. All right, moving on. No, actually, wait, there's more, a little bit more that I have to teach you guys. Okay. The most common scenario that you guys are gonna face when you guys actually no, something wrong. The most common scenario that you guys are gonna face is this. Something like this. This is a slope. The slope inclined at an angle theta, right? And there is a mass. There is a mass of mkg, of mkg. Now, the question will either say that the the mass is either going up, down, stationary, depends. But if you can resolve all of the forces that are acting on this mass, you can solve any question. For example, down, what it the weight's working. Okay, so completely vertically, we have the weight working, which is equals to we learned weight is equals to mass into gravity. Now, try to memorize this if you don't understand the concept. Right. The concept is this side becomes mg cos theta. This side is r. Right. So, and the slanted side, depending on, let's say for now, let's consider that. Okay, no. Yeah, yeah. Okay. So you can see that if the mass is free of any external forces, uh, there is a force acting towards the slanted left side. This becomes mg sine theta. Right. Okay. Now that's the main concept of this chapter. Can refer to this can refer to this as mass up or down, slope and resolving forces. Resolving forces. Right. So that's that's chapter 3. Now, moving to chapter 4, which is friction. Right. Now moving to chapter 4, that is friction. Let me use this. Hmm. Chapter 4. Wait, should know. Wait. Let's write it in a nicer way. Chapter 4, that is friction. Right. Okay. So friction is also related to chapter 2 and chapter 3 because it develops on that idea. It develops on that idea that um, what we use with resolving forces and slopes and everything. Now, here's the general idea. That is, okay, friction equals to mu into normal contact force. Now, you guys might be confused, like, you guys might be a little bit confused because you guys might think that, oh my God, what is mu? Oh, wait, my bad. Yeah, you guys might think, what is mu? Mu is the frictional constant. It's a friction constant which is usually given in the question or you have to find out. Right. Now, this is F is equals to mu R. Right. Now I'm going to draw the same diagram as I have drawn before. Now, let's say. Now think about this, guys. Think about this. Imagine this slope, the same slope. Okay. I'm going to use the same example. The slope at angle theta with mass m kg. This is going down, so it's gonna be mg. This is gonna be mg cos theta, and this would be r. Right. Now, since the slope is slanted left towards the left, we can see that if no force no external force acts on this mass, the resultant force would be mg sine theta. Now, this is considering that this slope is smooth. Now, in physics, we learned that surfaces can be smooth or surfaces can be rough. In this chapter, we deal with rough surfaces. Now, if surface is rough, this side will have a friction force. You guys feel me? Nice. Now, how to do this? We know friction is equals to mg sine theta because forward is equals to backward. Forward is equals to backward. Therefore, in the previous formula, we learned friction is equals to mu r. Mu r, which is equals to mg sine theta. Now, can anyone tell me what r is? From chapter 3, we learned, we know that R is mg cos theta. Make sense? Should make sense. So what we can do is, keeping mu as it is, mg cos theta is equals to mg sine theta. Cross out mg, then mu is equals to sine theta by cos theta. Mu is equals to tan theta. There you go. Most of the time, you don't have to remember this. This is a derivation that I just made to make things simple. 90% of the time, you have to solve. Okay, in the question, what can they ask you? They can ask you a few things. They can ask you to find mu. They can ask you to find r. They can ask you to find m. and they can ask you to find theta. Remember, they can never ask you to find g because g is it's a constant. It's a constant. In physics, g is 9.81, and in M1 it's we consider as 10. Right. Now, going to, as always, I'm gonna write down the meaning of the terms because uh so that you guys don't get confused. Right. Now, where were we? Right. Uh this this is straight line. Yeah, this is straight enough, I think. Yeah. Yeah. Okay. Okay. So usually what I do is I try to I don't write friction as I try to denote friction as FR, which means friction, which is Newton. Mu is um the frictional constant. This has no unit. Constants have no unit, if you guys know. R is normal contact force. Then what else do we have? We have theta is the angle of slope. Yeah, that's technically it. Angle of slope in degrees. This is in Newton. Oh, sorry, this is no unit. My bad. This is no unit, and this is in Newtons as well. Right. Now, this chapter wasn't that hard as well. Now, the thing is, I won't directly go into chapter 5 right now. Instead, what I'm going to do is I'm going to go to chapter 6. Now, actually, you know what? I think I can go to chapter 5. Hold up. Wait, I gotta check if I can. Because chapter 5 deals with certain concepts that might take some time for me to teach. Okay, actually, no. We'll skip chapter 5. We'll directly go to chapter 6. Okay, now, as I said, we'll skip chapter 5 because yeah, I have to really explain chapter 5. Because connected particles is a very complicated topic, and I just cannot draw the concepts. I also have to think 5 to 10 minutes to explain it. So we're gonna move on to chapter 6. Yes. Also, if you guys are wondering, yes, you can learn all of this. Like, sure, chapter 2, 3, 4, and 5 are connected. Um, 5 is still can be solved. I mean, 5 can still be learned separately, even though it does include forces that are resolved in components and also include friction. But don't worry, you'll see when I get to it. Okay. So, you get me? Right. There you go. So, chapter 6. So, what's chapter 6? Chapter 6 is general motion, motion in a straight, general motion in a straight line. Right. Now, this is a very vast topic. This is a very vast topic. This is a vast topic because sometimes it's very complicated. Sometimes it's super easy. Generally depends if you understand the question or not. Right. Now, I will try to write down the formulas or whatever you need because again, guys, this is very easy. This is very easy. You just have to know a few things. That is, S is equals to, let's say, distance is equals to ft. All right, t refers to time. S is displacement or distance. ds by dt is equals to v. Actually, I would, okay, no. Yeah, I think I'm comfortable. Okay, now, okay, wait. This is not how I wanted to write it. right? This. So let's S is equals to ft. It's a function, right? So velocity will be ds by dt, the derivative of distance. Now, acceleration is acceleration is dv by dt, the derivative of velocity. Now, similarly, should I, yeah, I think right here. Yeah, similarly, if you integrate acceleration, you get velocity and actually, yeah, wait, it's not writing like that. Yeah, v, and if you integrate v, you get uh, you get distance or displacement, right? So again, simply stating, um, you know this, s is equals to distance slash displacement in meters. V is equals to velocity. A is equals to acceleration, and t is equals to time. The thing is, this is a very straightforward chapter when you're learning it. The main issues actually arrive when the main issues actually arrive when you get to the question paper. So yeah. However, again, this is just a guide. Okay, this is something that you can refer to when solving question papers. But again, I do suggest that, when you'll be solving a question paper, you'll also have uh you'll also have someone helping you out, whether it be in your real life, uh whether it be your real life tutor or it be a YouTube video. But yes, okay. Next. Next is chapter 7. Now, momentum. This is also a very easy, straightforward chapter. No need to worry about this. Okay. For momentum, you have to know a few things. This is something you learned in O level. That is sum of momentum before collision is equals to sum of momentum after collision. Does this look familiar? This is also known as principle of momentum or principle of conservation of momentum. Conservation of momentum. Right. Now, this is very uh this is very simple. You learned this in O levels. Uh sure, A levels we went to a bit depth in AS, but there is literally it is what it is. You'll see what I mean. So go to formulas. You'll see M1 U1 plus M2 U2 is equals to M1 V1 plus M2 V2. That is it. Okay, you have momentum is equals to mass times velocity, which is then it is P is equals to mv. Right. All right. Now there are a few things that I'd like to add regarding this is this is not exactly in the momentum chapter. However, however, I'll still add it just in case because there have been question papers regarding momentum that have used this formula, but it's very rare. It is extremely rare, and This usually comes in work, energy, and power questions. Okay, that is okay. Do you guys know about this? I think you guys have learned about this in AS. This is the principle of elastic collision. So I think it is sum of kinetic. Oh my God, bro, I'm so bad at this. Yeah, yeah, sum of kinetic energy before collision is equals to sum of KE after collision. Right. I think this is elastic collision. So what you can write it as is usually written as half m1 v1 square u1 square. I bet should write it more nicely. So it's half m1 u1 square plus half m2 u2 square. Notice that even if your velocity is negative, the square makes it positive. So ultimately, it's positive equals to half m1 v1 square plus half m2 v2 square. Now, you can further break this. Okay, there's one more thing to add. It says plus loss in kinetic energy. Okay, this is if there is some kinetic energy left that the question has mentioned. It's usually very rare for such questions to arrive, and usually the questions where they include this loss in kinetic energy part is usually in the question 6 or 7, which arrive in which are regarding the momentum. Okay. If you guys are following the book, the M1 book that we have, I think this was somewhere found in, if I'm not wrong, you can check exercise 8B, 8B, question 11. Right. Okay, now, yeah, sure. Exercise 8B is work and energy, but again, it does apply to this uh, topic as well. All right, now you can further break this down by writing u1 square plus u2 square is equals to v1 square plus v2 square. Because try to understand something. That is this half can be taken common. M1, M2, M1, M2 can be taken common because these are constants. So, and break it down like this. And there is one more formula which further simplifies this, but I prefer you not use it. It is U1 plus U2 is equals to, oh my bad, is equals to V1 plus V2. This is usually not needed. This is not needed. You don't need it at all. Like, just it's just I gave it to you guys because there are some questions that are applicable for this, but usually you just don't bother with it. Okay. As an educator myself, it's my responsibility to just show you, but otherwise, yeah. So that's chapter 7. Now, moving on to chapter 8. Chapter 8. Now, finally, the big one. This is work and this is work and energy. Nice. Okay, so, you know, work done is equals to force into displacement cos theta. Okay, cos theta. If theta equals to 0, uh, then the whole thing is 1. So you could think of it as uh, force into displacement, but it's better to write as force into displacement cos theta. You can also write it as FD cos theta. Right. Now, there is a certain note. Note that, so two notes. That is, work done against friction equals to friction force times displacement cos theta. This is the same, which in equally comes as Fr times d cos theta. And number two would be, for once, number two, work done against normal contact force is always zero. I did not need to mention point number one, but since I did mention point number two, I wanted to like clear it apart. But it's pretty obvious because you guys are smart. You guys should know this. Uh, Finally, point number three. That is, might have to draw a bit of diagram right here. Watch this. Okay. Now, in some questions, what you're going to be asked to draw. Okay, wait. Not draw actually. Some questions are going to ask you to find work done against the gravity. Then that's going to be an issue. First, let me just draw it and then I'll explain. This is H. Let's say this part is D. This is mg. This is theta. This is alpha. Right. Now, work done against gravity. When you're working with friction, you usually take the distance d. Okay. However, when you're working against gravity, it is usually GPE or always GPE. So, which is mass times gravity times vertical height. Trust me, many people make mistake regarding this. Many. In the exam hall, you are going to be in the high stress mode. Small details are gonna go over your head. Okay, now you might ask, what if H is not given? And that's very valid. Then there's a roundabout way to do it. You're always, if you're not given H, you're going to be given theta, 100%. And if you're given theta, you can always find out alpha. Okay, because, you know, just draw the triangle. This angle is always going to be 90 degrees. So, you can always find out alpha is equals to 180 minus 90 minus theta. Right. Oh, wait. Oh, right, right. Oh, wait. Let me just do this in green. Oh, dang it. Right. This one. Alpha is equals to 180 minus 90 minus theta, or you can simply write as 90 minus theta. Okay. So what's the formula? The formula is mg d cos alpha. Remember it. This is also another form of GPE. Right. Now, there's more. This chapter is there are a few formulas. There are a few cases to work with. Then you'll also see that there's something called increase or change in kinetic energy. Increase, or they can say change in kinetic energy. This usually refers to del Ke, which is equals to half mv square minus half mu square. Okay, then uh uh okay, there's one more. Okay, the same formula will go here, the one that we did here. Just yeah. Okay. So copy. How do I copy this? Can I copy this? Not sure if I can. Should know. Okay, I'll just write it down. I still pretty new to this. Not sure how to do it, but we'll just learn later. Now, I don't think I should be wasting time. The video is already, I can feel it being longer than I want it to be. Okay, so I'll write it in short. So KE after collision is equals to KE before collision, which is half m v1 square half m v2 square is equals to half m u1 square plus half m u2 square. Okay, that's that. Now, yeah, okay, fine. There's one more thing. Potential energy is equals to gravitational potential energy, which is equals to mgh. Right. Also, one more thing. So, since you've learned the conservation of energy, should also I should also write this that gain in gain in potential energy is equals to loss in kinetic energy and vice versa. Vice versa. Hmm. Now, where do you think you can apply this formula? The application of this formula usually works when you're trying to find out the, let's say a mass. Okay, say a mass. It's right here. So you have to find out the energy at this point, the energy at this point, and once you find the energy, you might be asked to find this vertical height or this slanted distance if they give you if they give you the frictional force. So again, depends on question paper. Okay, it generally depends on question paper, but yeah, it is what it is. Just put this here. All right. Uh, okay, what's left? Oh, right. They can ask you things in this chapter in a roundabout way. For example, okay, let's say question says increase in height. This refers to gain in GP or loss in KE. And similarly for decrease in height is equals to loss in GP, gain in KE. Bro, I apologize if my writing is starting to become a little bit bad. It's mostly because I'm trying to make sure to finish this in time. Okay, all right. But yeah, I think we're two more chapters left. Do we have time? Yeah, we have time. Okay. We're within time. Okay. So, next, we're gonna be doing chapter 9. Chapter 9, that is the work energy principle and power. Work energy principle and power. Work energy principle and power. Before I start, I want to make sure that um I have given I've written the titles of most of it correctly, so I want to make sure. Have I? Yeah, I have. Right. Right. This is very important because I'll also be giving you guys the PDF of this. So don't worry about it. You guys can always look through my PDF. The reason I'm making this video is because there are many students who might not always feel comfortable seeing a formula. They want to understand what the teacher was talking about when he wrote this formula, if it has any deeper meaning behind it. Uh, because that's what I felt when I saw my formula book given by my teacher or when he was giving me his notes. So yeah, I think it's always best to have a guide. Not that you guys need it, I'm sure you guys, many of you are smart, but yeah, to those, I hope this video will generally be helpful. Without further ado, let's move on. So anyways, the first formula that we learn is sorry, actually I'm gonna write now. Increase in kinetic energy is equals to total work done by all forces. Total work done by all forces. Okay, therefore, okay. Increase in kinetic energy, we learned that it was half mv square minus half mu square, given that v is bigger and u smaller, equals to summation of force into distances. Okay, because work done by all forces, you can also write that summation of force into distance. Okay, right. And then there is another formula that is increase in mechanical energy is equals to mechanical energy. What does mechanical mean? A lot of people feel confused. Mechanical associates with anything moving. Okay, anything moving. Okay, so it's like, okay, think about it. What is mechanical engineering? Okay, mechanical engineering deals with things that move. So mechanical energy is basically total work done um by forces that act to speed up a body minus total work done work done by forces that that work to oh my bad that work to slow down a body. Okay, therefore E is equals to work done minus, okay, what does the arrows represent? The top arrow represent speeding up, the bottom arrow represents speeding down. Okay, I'll still write it down for you guys. Right, that is arrows represent speed. Right. Okay. Now, oh yeah, one more thing you should know. This is actually that came to my mind. Okay. Right. That is for this, right? For this. Okay. We exclude the weight of the body or work done by weight. Okay. Where should I write this? Okay, maybe I'll just write it here. Exclude work done by weight. Right. Because let me tell you something. When you're going to be solving a question like this, usually what you're going to be doing is, let's say, okay, this is very in general. Okay, this is you're not going to understand it most probably right now, but when you're doing the question paper, this will generally come to you. This will generally come to your head. So what you'll be doing is you'll be writing, we'll make a table, initial, final. Okay, you'll make a table. Okay, and in this table you will you'll write a few things: potential energy at initial, potential energy final, kinetic energy initial, kinetic energy final. Okay, if an external force is applied, let's say someone is pulling an object with a rope, then that would be um, force applied, or that's force applied, or let's say someone is let's say someone is um let's say if it's a car, then what? Then the car will have driving force. Okay, the car will have driving force. Okay, so you'll write the driving force, and finally in final, if the surface is rough, it'll always have friction. Okay, why am I writing friction in full form? It will always have friction. Okay, wait. Where did it go? Right. It'll always have friction. Now, what you're gonna do after you have this, you're gonna get the total, so total I, total F, and then sometimes instead of doing this, what you can do is basically instead of doing this, what I prefer is um therefore E is equals to work done final minus work done initial is what I do. Okay, that's that. Okay. Now, um, there is a little bit of more left. But yeah, I hope we should be done. We still have time, but I can stretch this video a bit more. Right. What else am I missing? Oh, right. Right. Okay. So I refer to this table when you're doing sums like this. And now, time for notes of this chapter, which are made by me. I mean, notes as in like footnotes, like the ones you have in books, history books. Okay, so again, let's say this is H, this is X. I'm gonna mention it again. The thing is, I already mentioned it once in the previous chapter, but I'm still gonna write it because people forget this. Work done by gravity's distance. That is H. And oh my God, right. And work done by friction's distance is X. All right, so that's that. Now a little bit more is left. That is, we still have, wait, now, next thing we're gonna learn is conservation Conservation of mechanical energy. Mechanical energy. This is very important. This is very important. You have to genuinely understand this formula. So please try. That is, okay, initial kinetic energy plus initial GPE is equals to kinetic energy at any point plus GPE at any point. Okay, this equals GPE at any point, which is also equals to final KE plus final KE plus final GPE. So again, this is the conservation of mechanical energy. This means, explain it very briefly. Okay, let's say point A, B, C. Okay, point A, B, C. Point A is initial, point B is final, and point B is, sorry, point C is final, and point B is just a point. Let's say it's any point. Okay, it's any point as in like anywhere. Okay, now you have to understand that um energy cannot be created, neither destroyed, right? So the GPE plus the KE that we have in point A is transferred to point B. It will also be transferred to point C. Okay, now you might ask that this looks very familiar, and what's the difference from the formula that we learned here? There is no difference. It's literally the same thing. This is literally the same thing. And my advice to students is, again, just use this table, the table that I showed you guys, this table. I'm gonna actually make it a bit nicer. Wait, this is not the right color. My bad, guys. Yeah, lit literally use this table, you guys should be fine. Like this is how I solved my exam, and trust me, my exam went great. Okay. Yeah. This is what you should use for every question. Okay. Yeah. Okay. Now, what else? Oh, I think I also have to mention this as too. This chapter also makes me include this loss in GPE is equals to gain in KE, vice versa. I know a lot of people are mad, like, why am I repeating some points? Guys, I'm really sorry, but this is a video, this is for everyone, so I don't want to miss out anything. I know most of it is common sense, and you guys will figure it out, but still, I like to be safe. Okay, 2 more minutes, for this chapter. Then we have power. The power is a very small part of this chapter. Just to know power is equals to work done divided by time, which is equals to force into distance divided by time. Right. Yeah, divided by time. And finally, we know that distance divided by time, force into d by t, force into velocity, just p. This is the new formula. I'm not sure if we used this in AS physics, but this is new. Uh, power of unit of power is watt. It's W. And yeah. Oh, there's one more note that I'd like to give you. Okay, no. Actually, yeah, this is for this chapter, and yeah. But Okay, before we actually move to chapter 5 or I start working on chapter 5, there's actually something that I'd like to go back to. Okay, here. Okay. Um, I want to modify this a little bit so that you guys understand a little bit better. Wait, okay, that's way too much. This is okay. So remember how I wrote just driving force or applied force? Yeah, I'm gonna change it to work done by driving force and work done by friction because a lot of people can misunderstand. Therefore, energy is fine, but it should be work done by driving force minus work done by friction is equals to um final KE plus GPE minus initial KE plus GPE. This is better. Yeah, I like this better. Yeah. Okay. This might be a little bad, but this is K. In case you guys were having a hard time understanding. Now, moving on. Right. Okay. Moving on to chapter 5. Connected particles. It's trickiest. Most people have a problem with this chapter. Okay. Now, connected particles. Okay, Bismillah. So, chapter 5. Okay, this is uh connected particles. Okay, okay, right. Right. Okay. Sorry, guys. I was checking something. I was wondering if I missed something, but no, I didn't. Okay. Now, connected particles. This chapter introduces some concepts that were in your AS level, I think during the 2020 to 2022 era session, but then after 2022 syllabus changed, one might say, or one might call it as the lift problem. Okay, watch. So consider that this is a lift, right? Consider this is a lift. Now think about this. Let's say, oh wait, my bad. Yeah, let's say inside the lift there is a man. There is a man. The man weighs has a weight of mg. Man has a weight of mg, and he also has um a normal contact force. Okay, okay, right. Let's say right now the lift is not moving. Okay, the lift is not moving. All right. However, when the lift starts to move, what will happen? It can either, there's two possibilities. It will either go upwards with constant velocity or downwards with constant velocity. Right. Now, now think of this. Think of this. If the lift goes upwards with constant velocity, okay, then, okay, sorry, my bad. Yeah, okay. The lift is going upwards. Okay, so the man same is here. He's here. It has weight which is equals to mg. Now, as the lift is going upwards, the normal contact force will be greater than the weight. Okay, therefore, R Therefore, R is greater than mg. We can say resultant force is equals to R minus mg. Okay, right. Similarly, if you guys are smart enough, you guys can surely figure out that in this scenario, just take this a bit down. Right, in this scenario, yeah, right, the man, if he's going his same weight and normal contact force, if he's going downwards with constant velocity, his normal contact force will be less than mg. Therefore, resultant force. So this is not correct. So it's, okay, right. Okay, resultant force is equals to mm, mg minus r. Okay, right. No, actually, I feel like there's one way to do about this. Mg minus r. Now, this is what we call the lift problem. Okay, this is famously known as the lift problem. In connected particles, you have three types of problems: lift problem, pulley problem, and I feel a system of moving particles. Yeah, I'm not sure what it's called, but yeah, we're gonna go with this. We're gonna go with, okay. Okay, I think I'm gonna call it connected particles in a system. Okay, now listen very carefully. This is the most trickiest one, the one where most people get it wrong. Okay, let's say between two connected particles, consider a train. Let's think of a train. Okay, everyone, let's try to imagine a train. And that train, let's say we have what we call an engine. We have an engine, and we have, uh, let's say, one of those sections of the train. Okay, okay. For easy, for easier for an easier way to say this would be, let's denote this as M2, and let's call the engine M1. Actually, and just write engine one. M1, M2 actually is referred to their masses, so yeah, there is no big. Okay, actually, no. It's okay. Actually, I can. I'm kind of wrong. I need more space to do this. Okay. It's not- Why am I getting it wrong? All right. Okay. So let's say this is the mass two, and and let's say this is the engine. Okay. Of course, they're going to be connected. Let's say they're connected using a non-inextensible string. This is very important. This term. Okay, remember this term. This is non-inextensible string. You know what this means? Non-inextensible string refers to string that has negligible impact on the whole system. It's very important for the question to mention this. Otherwise, we cannot solve our the question that is given. And don't worry, guys, all of the questions in A2 are non-extensible string. So No worries. Okay, or rope, whatever you like to say it. Okay, no worries. Coming back, I'm just gonna label engine M1, M2. Now, the engine provides a certain driving force. Okay, the engine provides a certain driving force. Due to this driving force, the M1 also moves this side. The M1 has a resultant force in this side, right? And if we consider there to be friction, then the engine will have F1 and the mass will have F2, or basically FR1, FR2. Right, let me write it properly. There's so many denotations in this topic. FR1, FR2, right? Okay, now, what's the bigger issue? Now, think of this entire thing in a system. Okay, think of this entire thing in a system because it truly is in a system. Okay. Oh, what? Okay, that was unexpected. Well, okay, this entire thing is in a system. Entire thing is working in a system. Now, coming back to the bigger things, what is the formula for everything? What do we do? Hmm. Net force. Net force is basically the resultant force. It's going to be driving force minus F. Okay? It's going to be driving force minus F. Now, since we know driving force minus F, we can say driving force minus F is equals to mass times acceleration, as resultant force is equals to mass times acceleration as per Newton's second law. Now, we can also write driving force minus F is equals to, oh, my bad. The main point. Okay, okay, listen. That is the biggest thing, the game changer. Engine 1, since it's moving towards the right, since it's resultant, it's to the right, its tension will work backwards. Okay? Its tension will work backwards. And as 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 tension as wait, yeah, right. This is going to be T1. Okay, right. So this is going to be T1 now, the different color. This is moving this side, and tension is going to be towards the right. Do you know something interesting? We say tension this, tension that. In this entire system, tension 1 is equals to tension 2. Yes, they cancel each other out. I'll show you proof. I'll show you guys proof. Okay, now. This is the general idea. If I were to break it down, by the way, I'll just add this, not considering frictions. Okay, not considering friction. Not considering friction. Not considering frictions. Okay. Now, this is the okay. This part that I explained is a general idea. A general idea. This is not how you'll do math. I'll explain it to you. So think about all the forces that are acting. Okay. All the forces that are acting forward, all the forces that are acting backwards. Okay. Let's go. Let's do this one by one. Okay. We know net force F is equals to mass times acceleration. Okay. This is something we know. So everything together adds up to mass times acceleration. Plus, by the way, this is something that I forgot to write, that resultant force is equals to mass of the both particles plus combined acceleration. Remember something, in connected particles, acceleration of both particles are the same. They're the same. Also, velocity, they're the same. Okay, now we know F is equals to ma. But what is F? We don't know F, right? Because we don't even know acceleration. So how do we find F? What is the resultant force? The resultant force, F, is equals to driving force. Driving force is forwards plus, okay, no, minus friction 1 minus T1. Now, because these two are going backwards, again, plus T2, it's going to the right, minus FR2. Oh, wait, I read. Yeah, minus FR2. Do you see something? Do you guys remember that I said T1 is equals to T2? Watch this. T1 and T2 cancel each other out. Therefore, the forces that are left with us are driving force minus FR1 minus FR2. Okay, by the way, some of you might wonder what this F refers to. This F refers to F is equals to T2 minus friction. Okay, this is that F. If you guys are wondering what this F refers to. Okay, now, since we also know this, we also know F is equals to dF. Okay, so now this at dF minus FR1, FR2. Using basically substitution, F is equals to F, we can say dF minus FR1 minus FR2 is equals to mass times acceleration. Acceleration of the combined particles is dF minus FR1 minus FR2 by mass. There you go. Now you might ask that, okay, sir, how do we find out the tension? Because they cancel each other out. Because in connected particles, of course, they're going to tell you to find tension, right? Yes, they are. Once you know this acceleration, once you know the combined acceleration, let's say, okay, you know something. T2 is equals to T1. In question, when they ask you to find the tension, mention this, or actually you don't have to mention this, but for your so that you understand I'm mentioning this. Okay, actually I'll highlight, okay, again. So T1 is equals to T2. The formula is very simple. Guys, I want you to think what looks simple. Engine or M2? Which has less forces? Okay. M2 has less forces. Therefore, okay, therefore, in order to find tension, you could do this. T2, because it's going forwards, minus FR2 is equals to M2 times combined acceleration. T2 is equals to M2 times A plus FR2, and that's your answer. And that is also equals to T1. Now, if you wanted to, let's say you're like, no, sir, we don't. like we don't like T2. We want to use T1 because T1 seems like it has more numbers. I know there are a lot of people who like to find who like to find a certain value or certain constant when there's more numbers to work with. Simple. However, T1 is a bit different. You have to realize that T1 is going the opposite direction. For T1, you have to do this. Driving force minus FR1 minus T1 is equals to M1 times combined acceleration. Therefore, T1, T1 is equals to dF minus FR1 minus M1A. That is the answer to all of this. No, oh, my bad. Um, okay, actually, I would want to make a box. I'd rather highlight it. Nice. Okay, there you go. So we think this is, oh, finally is the pulley problem. The pulley issue, right? Okay, finally we come to we come to a conclusion. It's a conclusion which is not technically a conclusion because I'll tell you something. Pulleys can be of many types. There are hundreds and thousands of types of pulley questions. Okay. However, I'll show you two types. Pulley problem. Pulley problem is literally the same as this problem because because in a pulley the particles are also in a connected system and a singular system, and the tensions are also same. Okay. Um, but not always. You'll see what I mean. Okay. Before I start, I'm just gonna give one advice. Must do 2020 to 2026 topicals. Okay. Right. Now, the pulley. Let's say this is a very special case just to explain to you guys what a pulley does, basically what type of question they give for a pulley. We try it first. So let's say this is a slope. There is this, I forgot what this is called, but this is basically the one with the light extensible rope that holds the two particles. Let's say this is B, and let's say let's say A. Okay, this is A. Right. Okay. Now, let's say this distance is X. This distance is also X. This distance is L. Right. Now, I'll tell you guys the general thing. Um, copy this diagram again. I cannot wait. Right, I'll copy this diagram again. Now, okay, right. Here we have particle B, and here we have particle A. Let's say M1, M2, and we're assuming M1 is greater than M2. Usually M1 is always greater than M2. When B is released from rest, usually both particles at first are at rest. Okay, tension works here, T1, and tension works here, T2. As B goes down, A moves forward. A moves forward. Similarly, as we saw in the last question, what we can infer is, oh, of course, there is weight, right? There is weight. So this is weight, right? And of course, this might have friction. So this is friction. Okay, this is friction. So, uh, if it's smooth, then there is no friction. But again, I'm calling this a rough plane because more more variables help will help you understand better. Okay, right. So, of course, weight minus tension 1 plus tension 2 minus friction equals to m1 plus m2 times acceleration, which is the combined acceleration. T1, T2 cancels out. M1 weight minus friction is equals to m1 plus m2 times acceleration. What else? Okay, yeah, same. And if they tell you to find tension, simple. What you could just do is when they tell you to find tension, T1 is equals to uh, T1. Oh, yeah, sorry. Yeah, I will. Yeah, right. Weight minus T1 is equals to mass times combined acceleration. So weight minus mass M1A is equals to T1, which is equals to T2. All right. Now, the certain note that I'm going to give you guys is in such cases, when B drops to ground, A moves X meters with combined acceleration. But A moves the remaining L meters with new acceleration, mostly negative. You have to find, usually the questions usually tell you that you have to find L. You have to find L or the total distance that is traveled up by A. Since the question usually gives you X or it doesn't, you have to either way find out. And what you have to do is during L, you will know something. Either you'll know the final velocity or the initial velocity. You'll know something. Oh, you okay? There's one more thing. Yeah, you'll know the information will be given in the question, and once the information is given, you will use uh, formulas from chapter one to find out the acceleration. And then once you find out the acceleration, you can easily find out the distance using v squared is equals to u squared plus minus 2as. Right. I hope that makes sense. Again, you will see these questions when you do question paper. There is no definite way to explain you these certain scenario questions unless and until you're doing question paper, because this is very question paper specific. You guys have to understand. For example, for example, till now we have been working with the fact that T1 is equals to T2, right? We've always seen for our question that T1 is equals to T2. Let me show you guys something. That is, let me tell you guys something. That is, there are questions where there are questions where you have something like this. Very special case. Special case. Okay, so what's the question like? All right. Um, here is this. So this is like this. And we're just gonna okay. All right. Oh, I remember. This is called pulleys. Oh yeah, the pulley, right. Okay. Okay. Let's say this is particle. This is particle B. Okay. So extended, extended. So here is a pulley. Okay. And let's say here is particle A. Okay. So this is again a pulley. And this is particle C. Right. You will see questions where there's T1, there's T2. There are two types of tension. And let me tell you, the way to solve this is completely different. Therefore, I'm just going to say note. Sorry, my bad. My bad. Yes. Okay. Note. Pulley questions are very question paper specific. You cannot pinpoint anything because there are cases where they match pulley with momentum. Sometimes they match pulley with work energy power. It it is one of the hardest uh, topics of A2 mechanics, and most of the time people lose marks here. Okay, with this, I think I have explained most of. Okay, with this, we're done with all 9 topics. However, we are not done yet because there are some special cases and extra things that I will like to note down for you guys, which you guys should keep in mind. So yeah, uh, let's go. We're gonna call them. We're gonna call them, right, extras. Extras. Okay. Um, right. Okay. Now time for extras. Right. So what the basically the extras are things that come in question papers or are some concepts that are not in our book, neither in our syllabus, but I have seen them come here and there, or concepts that you can use when things don't work out. So first of all, I'd like to start with wait, yes, I'd like to start with Lami's rule. You can actually find this in chapter 3 in our book. Okay, actually, it's not called Lami's rule. It's called Lami's theorem. The reason why I did not mention this earlier in during when I was explaining chapter 3 is because that barely any question I know has used Lami's theorem. However, I'll explain it right here, very simply. Just watch. So let's say you have middle, one particle. There's one extension here, one extension, and one extension this side. Okay. Okay. Let's say this is A, this is B, this is C. Let this angle be beta, let this angle be alpha, and let this angle be gamma. Right, gamma. Okay. Now, the general rule is A by sine alpha, B by sine beta is equals to C by sine gamma. Do you guys see the relationship? The relationship, very simple to notice. C is going this side, the angle that's going this side. So C by sine alpha. B is going this side. Beta is going towards the top left, so this side. So B by sine beta. Similarly, A is going this side, alpha is this side, so A by sine alpha. This is very similar to what we learned in AdMaths, IGCSE, which is the sine rule, but not really. Anyways, a more sophisticated way to apply this is to resolve the forces. Okay, what do you mean by resolving? Okay, let's let's draw the arrows. Let's draw A. A is going this side. Okay, this is this is A because A is going this side. Okay, all right. Then okay, let's draw B. Okay. B is coming this side. This is B. All right. Okay. Um, that's B. And this is considered C because it's going this side. Right. Now, how to assign the angles? Think about this very slowly, very carefully. Okay. So we know that A is going towards the left. Draw a line from here. Okay. So we can see that this angle is beta. Why? This angle is beta. This angle is alpha, and and this angle is gamma. Very simple. Okay. Okay. A and C. Between A and C, you have angle beta, as we can see from the left-hand side. Between angle A and B, we have gamma, and between B and C, we have alpha. So that's how we resolve. And um, there's one more thing that you should know is a lot of people forget this is the cosine rule. Now, most I know most people didn't forget, but still I'd like to mention it because it is in our syllabus. So it's A, this is B, right? Actually, never mind, I want to draw it a different way. This is angle B, and this is angle C. Right, so A, B, C. Cosine rule states cos A is equals to B square plus C square minus A square by 2BC, which can also be written as A square is equals to B square plus C square minus 2BC cos A. All right, right. Throw in an example, I guess. Okay, this is an example because even though Lami's rule seems simple, a lot of people find it difficult. Okay, let's say you have, of course, let's say you have a point in the middle. This is, let's say, 40 Newton. This is, let's say, 50. And let's say this is F. This is alpha, and this is 120. What you can do is, to find alpha, you can write 40 by sine alpha is equals to 50 by sine 120. Sine alpha is equals to um 50 by, no, actually this is wrong. Yeah, alpha is equals to um 40 sine 120 by 50. Alpha is equals to sine inverse of this. 40 sine 120 by 50. Right, that's that. Now, to turn this into a triangle, turning into triangle. Turning this into a triangle would be to Okay, and finally 3. All right, let's say this is 50, this is F, this is 40. Right, this is going to be X. Okay, between F and 50, we have alpha, and between 40 and F, between between sorry, yeah, between 40 and F, we have 120. Yeah, between 40 and F, we have 120. So yeah, and then you know, using we can also use. I think we can also apply cost rule if you find out these angles. Find out these angles. Since you already know the sides, it's not very difficult to find the angles because you can just subtract 180 minus alpha, and this is like 60 degrees. So yeah. So yeah. Now, what's that? And yeah, that's Lami's rule. And one more thing, this Lami's rule is for chapter 3, 4, 5. Chapter 3, 4, 5. No, there's some more. This is just for chapter 3, 4, 5. We have a few more notes that I have to give you. Oh, okay. Actually, can I? Yeah, I'm gonna do something. That is, I'm gonna move this down. I want to move this down because of what is this? Why did I make this? This mistake. Yeah, it's extras. I want to start with a little bit of note. That is, most people need this. Hmm? Yeah, it says if answer has exact decimal value, then give inexact, then give the full value with all all decimals. Okay. However, for continuous value, use three significant figure or 2 decimal places. Yeah, this is my note. I feel like I took this down a little bit too much. I'm gonna bring it back up. Wait. Bring it back up. Not this, not so up, but yeah, I think this is better. Yeah, this is better. Right. Oh my god. Oh yeah. Okay. Wait, I think I made a mistake. That is, Excuse me for messing up. This should be good. Okay, here. A little bit more down. There. Yeah. Okay. Nice. Yeah, now it looks proper. Now it looks prim proper once again. Okay. Yeah. 50. Okay. All right. What's next? Now, anything more to do with connected particles? Not really. Oh yeah, there's one more special case. That is, you will find in the forces. That is anyways. Yeah, again, in some CH345 special, again, is something, you will see that there is a slope with theta angle or alpha angle. Force, let's say this is an object, force is applied in this direction. Now, I could explain you guys the concept, but you just have to know. Uh, right, right. You guys just have to know that resolve it this way and this way. This becomes f sine alpha. This is f cos alpha. Okay, and then you can solve it. This one specific sum came in the year 970942, May, June 24. I think one more sum like this came in, if I'm not mistaken, I think this also came in 2022 or 2020, but I don't remember. But yeah, okay. Then what else do I? Okay, yeah. Then there's more. There's one more. That is, let's say, let's say, let's one, two. It's a point. Let's say this is x. Okay. Let's say here's one. Here's two. Let's say this is tension one. Let's say this is tension two. Okay. Least value of x. When they tell you to find the least value of x, you have to consider that t2 is equals to 0 if block remains at rest, and therefore 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 t1, oh, this is mg, t1 is equals to t1 is equals to 10, t1 is equals to 10m, because mg acting downwards. Now, it's very hard to imagine this, but think of it like this. Let's say T2 is 0. If T2 is 0, so this is the particle. This is x. This is mg. Then this becomes tension. Because you have to equate it, right? You have to equate it somehow. Uh, However, I do not encourage anyone to follow this because, again, this is very question paper specific. So please use whatever concept you guys have. This is a scenario that I saw. I don't even remember the year, but this one was a very tough question that I faced. Okay. Oh, and one more thing is something to do with the wording. That is, if ever a question says slack rope, it means that it has no tension. Okay? All right. Okay, what's next? I think I got most of it down. Okay, I think I have one from momentum. Yeah, I have one from momentum. Okay. Momentum special. It's not actually for momentum, it's for any particle that is released after some time. For example, the question is phrased like this. If particle A crosses point O, which is the origin, and particle B crosses point O after 4 seconds, then in order to solve the questions from then on, you have to consider this. Time of particle B is equals to T. Time of particle A is equals to T plus 4. Or if you want to assume that time of particle A equals to T, then time of particle B has to be T minus 4 because it is because you're trying to assume that they are uh, moving this they are trying to catch up to each other. Okay, all right. So that's the whole thing. Seconds is T seconds. Any more thing? I think there is. Oh yeah, one last thing. Yeah, finally, this is um straight line special case. Special case. No, no. Most of the time, you'll be told to make. Most of the time, what you'll be told. Wait, sorry. You'll be okay. There are few things that you will be told in such questions is you'll have to draw a velocity time graph or a displacement time graph. Okay, and eventually, certain questions will lead to one thing where you'll be using differentiation, and finally, they're going to tell you to find the distance traveled from certain time to certain time. For example, now most of the questions are straightforward. However, one or two questions I found were kind of it tested the brain that people or that students didn't understand. For example, this point, let's say this graph. Okay, this graph. Okay, this graph has three sections. One, two, and three. Right. Let's say this is point X, this is point Y, and this is point Z. Okay. To let's say they tell you find the total area under the curve. This is how you have to do it. You can't just you can't just say integration of velocity from sorry. You can't just say integration of velocity from 0 to Z. It doesn't work like that. It is dead wrong. The correct method to do this is first S. You have to find distance from 0 to Y. Okay? Plus. Then you have to find the distance from Z to Y. Why is this? Because because this Sorry. This is negative. This is negative. Um, so when you give the limits from 0 to z, you don't find the total area. You find, I mean, it subtracts itself. This area becomes subtracted. Okay. It's more like you're finding displacement. Okay. All right. Basically, total distance area, whatever. Total area means like the total distance, right? You're not finding the distance. You're finding the, okay. All right. Sorry. Again, I'll say it again. When it says find the total area under the curve, they mean distance. When you do this, doing this equals displacement. You don't want to find displacement. You want to find distance. Okay. Hence, you have to make sure that whatever value you get, the negative value, okay, let's say, uh, okay, let's assume again. Once again, we're assuming. Let's say this is 43 meters plus. Let's say this is minus 31 meters. What you have to do is you have to modulus this, and then it becomes 43 meters. Example given plus 31, which is equals to 74 meters. Okay, that is our distance. So guys, that's it. That's for the video. That's the entire thing. That's the entire A2 mechanics syllabus covered from A to Z. Again, guys, this is not a master class. This is more a revision guide, which I want you to note down in a small notebook or a notepad, or if you wish in your copy, or if you guys are using tablets like me, then your tablet. And when you're solving question papers, if you ever get stuck, let's say your teacher gave you a question paper, she's helping you solve it, but you don't understand something, you come back to this, you understand the concept. First, try it yourself, understand the concept, and then try to solve the question again. If you can't, then there's always ChatGPT, Grok, and so many videos in YouTube that'll help you. This guy's the video comes to an end. Thank you so much for sticking around, and I will catch you guys next time. Inshallah, Allah Hafiz.